like really rich pepper.
Are you?
Just in the shells. You know what I mean? Like every all the bloody cooking nuggets, we're all like, well, why do we do that? Like that, you know, we do those. But we just keep noticing because the bottom shelf is all really fine. They go top shelf. Yeah, the thing was broken, we fixed. So yeah, but on one side, like on the left side, and then when it broke this time, it broke off on the right side. Yeah. Like, so like, it's just, you just have to follow it. I just kept trying to, yes, I'll be home. So, Marshall had the version of it. Oh, yeah, exactly.
Good morning. Sorry to be taking your seat. I recorded today's session on my own end. So you can sit anywhere you want. Good morning, Joanne.
So I'm like, you cannot put it up. You cannot put it back. It's just get me. I wanted to tell you.
Okay, you've got 8:30, so why don't we get started? Good morning, S&P.
Good morning.
Yeah, that's pretty good. Week number 7. Hope you all had a glorious weekend. Looks like the sun has finally come out after all of that rain. A couple of announcements today. First, I want to thank you all for your excellent writing assignments. You turned those in on Wednesday, and I was grading them over the weekend and just finished up 1 or 2 of them this morning and put them back in your Slater box about a half hour ago or so. So your writings are back into your Slater boxes. Thank you for your good writing. One notion about that, some of you might know from another class that when I'm providing feedback on writing, what I'd like to do is have a list of all of the most commonly occurring ways to improve on a writing assignment, and I have 22 of these items. They're shown in green, and I attached that to the back of all of your writing assignments, and you can take a look at those and see how you're doing. A couple of suggestions for how to make improvements and so forth. So that's in there, and that's available to you. Also, in some cases, you'll notice that there's some information on that sheet that suggests that your writing might be improved in different kinds of ways that can be accessible to you by way of 2 PowerPoint files that we have out on the S Drive and Blackboard. These are called writing tips, and people in my other class know all about the writing tips. But the writing tips are there to help offer some additional information about how to make things clear. So you might see as you're going through your assignments that I've put a number 8 or a number 4 or a number 6 that refers you to the green sheet that's attached to the back of your writing assignment. And then that will help you to understand where I think some clarification can come or some modification might come. But overall, these are really terrific. And that was not an easy assignment, trying to synthesize these very unrelated topics, but I thought people generally built their bridges very effectively. So thank you for that. I really enjoyed reading those. And we had a great conversation the other day about that. Okay, I've got some really good news. Today is October 7th of week 7. So you know what that means. Friday's going to be exam number 2. Can we give it up for exam number 2? Yay! All right. So what do we know about exam number 2? Out here on the S Drive, I have about exam 2, and this is available to you also on Blackboard. So this format is basically the same as we had last time. We'll have the entire period for the exam. The format will be almost entirely short answer, and you may have to draw some graphs. Just to get that conversation going a little bit, can somebody tell us what we would have on our axes if we had a signal detection theory graph on the y-axis and on the x-axis? What typically goes over here on the y-axis?
The percentage of photons.
Oh, okay. Actually, it's not. That would be what we would be using if we had our filters, right? The percentage of photons. Okay, so this is the signal detection theory graphs. Anybody? Yeah. Marcia, discuss.
Frequency?
Frequency of occurrence, yeah, or probability, something like that, okay? And then on this axis, anybody want to help us out with that? Yeah.
The level of neural activity.
The level of neural activity. Another way of thinking about that is either the level of neural activity, or if you like, the sensory evidence level. So on the left side, we have way more sensory evidence. On the right side, we have less sensory evidence. I can even put that on the board if that helps us. It's really a different way of saying the same thing, but it might buy us something. If we say sensory evidence. So here's our signal detection plot. Here's our probability, or as Harshi just said, that could be frequency. And then this is neural activity. But we can also think of this as sensory evidence. If, for example, I have a lot of neurons firing, I've got a lot of sensory evidence. If I have fewer neurons firing, I have less sensory evidence. The reason why it might be advantageous to put sensory evidence there is that if we think about extrapolating from signal detection theory to other kinds of scenarios, this might be now a legal system. We wouldn't be looking at sensory evidence, but we might be looking at other kinds of evidence, right? Or evidence for maybe if we have some other type of format, we're always looking for evidence. It wouldn't just have to be neural activity. In S&P, when we're making these physiological recordings, it turns out to be neural activity, but it wouldn't have to be that. Who's following that? Okay. All right, so that's all about drawing graphs. All of this is the same kinds of content. I did add one line that I'll call your attention to, and that is the exam will be cumulative, but it will emphasize material since the last exam. And we had an exam on Friday, I guess that was the 19th of September. So new material started on Monday, September 23rd. That's when the new material from this section began. Okay? So that's what the emphasis will be on, although we actually introduced something like this way back when. Right? So it's cumulative, but the emphasis will be since the last section. And that'll be true for all of our section exams throughout this semester. Okay? Yes, please.
So should we study everything for exam 1 again?
Everything you could, you might be, that might not be the best use of your time, right? But I think it would be helpful to think about the threshold graphs. It would be helpful to think about maybe some of the overarching theories can be helpful. We talked about structuralism and gestaltism and ecological optics and things along those lines. That might be generally helpful, but the emphasis is going to be since the last time. All right, and how to practice is the same as what we had the last time. This is available to you on the S drive and also on Blackboard. Questions about any of that? Okay, real good. Just as a heads up, there's a chance that some folks might be floating in. This is a prospective visitors day, and so some people might be coming in, although they don't usually direct them to upper level classes like this, and it is 8:30, so, so we have two things working against us. Maybe we won't get any visitors today. Okay, here's what I thought we might do. Why don't we pick up on something we started the other day. We ended with PowerPoint's lecture color vision wheel. Let's go to that, go to here. Okay, and we can create different kinds of colors here. Probably a little bit better with the lights down. I think we get a better view of the color. All right, let's see if we can turn on the color wheel. You tell me, how do I get this going? Anybody want to direct me? Right click?
To the bucket that's on
The
the
bucket,
board.
okay. Here's our bucket, right? So we might go to here. More fill colors, then what do I see? Maybe I'm there. Okay, okay, I'm there. All right. Let's see. Let's see if we can create a really good yellow. Remember that we have red, green, and blue as our possible guns. So how did we get a really good yellow gun? Can we yell it out?
Less red.
Less red?
And drop the blue completely out.
Drop the blue completely out. So maybe I can hit a 0 here. Okay. And I'll go up to this one. Okay. And now here's the color that I'm forming. It might look darkish. There's a little bit of green there, maybe a dark olive color. If I want to get a really salient yellow, what do I do?
Raise in
I can go from 0 to 255. What do I want to do with red?
255 red.
Okay?
255 green.
255 green. Okay, and that gives us really good yellow. All right, so we can see. Now, what was cool about that was a metamer of sorts, and we'll come back to metamers later today. Now, what can I do to maybe get a really good, and this is how we ended the other day, this is just a review, how do we get a really good Hershey's chocolate? Some notions about this?
Take the red and the green back down to
Around 125.
Okay, let's take them both down to 125 and see where we are. Whoa. Did the right thing. Then go back over here with my right click and more full colors. Okay, 125, that might be a little too green. Is that what we're thinking?
Yeah.
Blue.
Reduce green around
40.
Yeah.
40 for green?
Blue.
Oh, bring blue up a little bit.
Yeah. desaturated a little bit.
Reduce green around 50.
Maybe a little more green and a little
Try that one, 50.
less.
That's pretty good. Yeah. I think that's pretty good. It looks a little reddish, maybe, but I think that's pretty good. Okay, so that's where we were last time around. All right, any questions on the color wheel? Yeah.
When you go to the more fill colors, it says color mode, RGB mode.
Okay,
I
let's
know
go.
that's red, green, blue, but
Yeah.
what else is there?
See what else?
The cyan, yellow.
More full colors. Okay.
Color mode.
So color model is RGB, right? And then there's other.
Hue saturation.
Okay. Oh, this is hue saturation and
Yeah, that's kind of fun. Want to play with that?
Okay.
Okay, what do we do with hue?
50.
That's cool. I think this thing moves around for us. Let's see if we can get it to go. Let's put it in 255. That brings it all the way over. So hue appears to be left, right, maybe? Is that what's going on?
Yeah.
Hey, that's pretty cool. All right, pretty cool. How about saturation? What's going to happen when I start clicking on this? Which way is it going to go?
It's gonna go up and down.
What happens with luminance?
No, it's on there.
Okay.
Oh,
All right, pretty cool. Pretty cool. Hue saturation and luminance. Very good. Thank you, Harsha. That actually never come up before. We're always dealing with the RGB typically, but that's another way of doing this. Pretty neat. Pretty neat. Yes, please.
I know that SM and L cones can't be directly translated to like red, green, blue, but
Right.
did you think of these three kind of as representing S cones, X cones, and L cones?
The three that we had a moment ago, that the hue, saturation, and lightness, which three are we talking about?
I guess the red, green, blue.
Red, green, and blue,
Yeah.
right? Yeah. Actually, it's a very interesting bit that we don't have a complete match between RG and B and our three different cone sensitivities. Does anybody remember the peak wavelength sensitivities for the three different cones? It was on a slide, not for Friday's session, but for I think last Monday's session, if I have it right. No, I'm sorry, it was Friday's session. 440,
440.
440,
530.
30, and
560.
560, right, okay? All right, so those are the various cone peak sensitivities, 440, 530, and 560. And what's interesting about that is that those don't really make a very good match to red, green, and blue. And so that's a bit of a mismatch. Okay? And yet somehow we do see red, green, and blue. I think the problem there is we probably shouldn't be calling those cones the red cone, green cone, and blue cone. Right? They're just the 530, the 560, and the 440 cones. Sometimes we call them long, medium, and short wave cones. Okay? So let's get back to your question, which is something like how do we get a red if we don't have a 5 or a 650 kind of cone? How do we get to see red? Is that where you're going with this?
Yeah, I guess kind of just a general correlation between the red, green, and blue levels, if there is one at all.
Yeah, there actually isn't a very direct one.
Okay.
What we can say is we do get more long wave red when we turn this one on, and that will activate more the 560 nanometer cone than any of the other two. And the psychological correlate of that tends to be red, okay? But there isn't a direct correspondence between those and the three cones. Yeah, please go ahead.
So, the only other way to get a red color wouldn't necessarily be to just like send out a wavelength of light that's exactly whatever it is, 560, whatever.
Yeah, actually 560 isn't going to generate a really, really good red for us, right? So what you have to do is you try to isolate that one, maybe by putting out a 700 nanometer light. Then you would get some firing in that longer wave cone, but no other firing in the middle and the short.
Yeah, another way to get a perceptual color aside from just sending out a specific wavelength of light is to have several wavelengths kind of spaced out.
Okay.
Where there are several different wavelengths that you can detect individually, and those mixing together will give you a perceptual sense of red.
I'm not sure what you would mix to get a perceptual sense of red. You can do this for yellow, for example.
Yeah.
So yellow, that would work, right? Red might be too far out, given our cone structure. There's another hand somewhere, I think. Maybe not. Okay, yeah.
So when you get into that, past the blue on that color gradient over there,
Okay.
can't you not create those colors with one wavelength of light? Don't you need like a combination of a low frequency and a high frequency to be able to like experience magenta?
Yeah, we're going to need a couple of those, at least given this mechanism, given that we have just 3 different guns coming out there, we are going to need some combinations. Yeah, please.
Sparked a question. Does that mean that purple or violet is always going to be a metamer because there is no one wavelength for it, or?
I don't know if I would say, so for it to be a metamer, we actually have to have 2 different stimuli. And we have to say, here's stimulus A, here's stimulus B. Can you make a same different judgment and get a D prime that's greater than 0, right? Okay. And if you can distinguish them, then they're not metameric. If you can't distinguish them, if D prime equals 0, then they're perceptually indistinguishable, even though they're physically different.
But in light, for example, well, I guess you can make violet.
Yep, we can. In fact, we can probably click on a violet over here somewhere. Is that working for us? Is that a pretty good violet? Let me go back over to RGB, and a violet might be something like. Try this. I don't know if this is going to work. Take out the green, put it in 200. Is that about right? Yeah. Okay. Now we wouldn't call this all by itself a metamer. Right? That could be one stimulus, and then we could put up a different stimulus that has maybe a very different composition, and ask whether somebody can distinguish those 2. And if they can't, then we have a metamer. Right? So we have these physically different stimuli that are perceptually indistinguishable.
But isn't like the screen is like composed of like different stimuli, but they're so small that we can't just like they're just
They're
like
small
little,
pixels?
Yeah, they're small pixels.
Okay, right. Uh-huh.
And so like in that sense, wouldn't like that combining be a metamer, or would it not?
So it is the case that we've been talking about a type of metamer. Where we have physically different stimuli that are perceptually indistinguishable. And we've taken some cases here that are really tremendous cases of metamers, because if we do, for example, this 255 and 255, we come to a yellow by 0, this guy. And that's very different from the 590 that I had on the other day, right? Okay, so there's nothing 590 in there, yet we get a compelling yellow either way. So we have this kind of a spectrum versus that, and those are very different stimuli. I think what you're asking is a very interesting question. You might be able to see that we have these tiny pixels here, right? Okay, and we can't distinguish a screen that has tiny, tiny pixels from one that's perfectly continuous, right?
Yeah.
It could be the case that we have such a good-looking camera up here, such a good-looking projector, that we can't even tell if this is a window or if it's a projector, right? I mean, it's so good. Now what happens there is that is a type of a metamer, because we can say that this isn't actually continuous. It has these discrete pixels that we can't discern. And we can't tell a discrete pixel representation from a continuous representation, even though they're physically different. So we could say that that is a type of metamer because it satisfies the definition, and those are physically different stimuli that are perceptually indistinguishable.
Right.
So as on your cell phone, you might have screens that have really good resolution, and they're looking really great as if you were almost looking at a small window or something like that, right? So that's a type of metamer. Some people, and this is very subjective, will tell you that's a metamer. It's also a very boring metamer because it's kind of like saying, well, any biological system has to have some limit to it, right? That you won't be able to resolve anything perfectly. So we're taking advantage of maybe the resolution limits of the visual system. What's a little bit different is when we do this yellow demonstration, normally that red wavelength, that green wavelength would be very, very discriminable, and I can show you that. Let's go back over to here. More 4 colors. So if I show you just red, that's really discriminable. If I show you just green, that's really discriminable from that yellow. So either that red or that yellow is very, very discriminable. So what's really cool about this particular brand of metamer is that they're not pushing against the resolution limit of any biological system. We're giving you wildly different stimuli, and yet somehow they're perceptually indistinguishable. But I think you're right. I think it's fair to call this a metamer.
But you can't necessarily say that violet will always be a metamer just because it doesn't have its own distinguishable wavelength.
I think the reason why I would say violet is, why you can't say violet is not a metamer, or violet is a metamer, is we always need 2 stimuli to make the comparison.
Right.
So violet is one color, okay? Violet is one color. I wouldn't say that yellow is a metamer. I would say that this stimulation versus that stimulation is metamer.
Yeah.
Okay, we have 2 sets of stimuli. Okay, to make the comparison. I like your example. We can talk about this being a continuous window. That's one stimulus. we can talk about this being discrete little windows, 1 pixel wide. That's stimulus number 2. Stimulus 2 and stimulus 1 are metameric. Okay? The word violet is, or the color violet, is just one thing, right? It's just one thing. Okay.
Yeah.
Yeah, go ahead.
Because I think we're trying to get at is that you can have like 2 and 3 different wavelength metamers of violet, but you can never generate violet with just one wavelength, because we've been, giving examples of, just the 590 nanometer versus the red and the green, whereas with violet you wouldn't be able to have just like one wavelength of light creating that violet.
Okay, now could you be able to do that? I don't know if anybody has a violet in here. That's pretty close in terms of the ways on. That might be as close as we get. Maybe that's a little bit on the pink side. Let's see if we've got that. Yeah, that's kind of pink. Okay. That's pretty close.
Yeah.
Okay, right, all right. Now, I do have my light meter here today. We're going to do some light meter demonstrations. Okay. Unfortunately, I don't know if it's going to be able to have a aperture that can get just June's portion right there. June, can we put that here?
I can always just use it.
Right. Yeah, we can do the, and then I can hit it with this. We'll take a couple of measurements in a moment, and we'll see that that might be fairly well localized. So pigments tend to put out generally one wavelength of light, especially if they're saturated. Right? That was the idea about hue saturation. Okay? But lights, sometimes we're going to need combinations because we only have 3 guns there. Right? So that could be saturated, and my guess might be that could be saturated down at around 480 or something like that. Okay, so I hope that helps, that we have this idea of metamer, and that's always going to require 2 stimuli, that there's a difference between having pigments versus having lights. Okay? And we'll go with Lisa's question next.
So if a color is desaturated, will you pick that up with the measurement tool?
Yes.
So if it's a desaturated yellow versus a 590 yellow?
Yeah, you might be able to pick that up. Right? If you begin to broaden the band on yellow, it's hard to know if that will still look yellow. We can do that experiment if we had control over the full range of these.
Yeah.
Go ahead, Archie.
So like we once did that in the center of our retina, near the fovea, we have more small receptive fields.
We have very small receptive fields
And
in
then
the
as
center
we
of
go
them.
down, we get larger receptive fields.
That's correct.
Is there any distribution change in Northern homes?
Yes, thank you. Very strong distribution change. So we get, as you go more eccentric, away from the center of the eye, away from the fovea, then you tend to get more rods and fewer cones. Okay. One of the ways I think about that, this might not ring true for your generation or even my generation, but my parents' generation, when they were kids, TVs were around when my parents were kids, but there weren't that many TVs, and they were almost all black and white TVs in the 1930s and 40s. Okay? And only the really rich people that lived in the best neighborhoods got to have color TVs when they came out. So you can think of color as something that's really quite specialized, and that there are fewer of those, and they're only going to be in the rich person's neighborhood in the center of the eye. As you move out into the periphery, you wind up with these black and white TVs, okay? The rods, that you might think of it that way, okay? As a mnemonic. All right. I did want to get to another portion of Friday's conversation, unless there was other questions on color wheel. That was fun. Those were great questions. And it is interesting the views about how these colors come about, whether we're using pigments versus whether we're using lights. Okay, I wanted to go to this thing and give us another way of describing our color experiences. We have the color wheel that we can use. And then I wanted to introduce a mechanism for describing quantitatively the different colors that we see. And this is going to be called the CIE coordinate system. Okay, so CIE is the Commission Internationale des Éclairages. I think maybe your French is better than mine. But many years ago, there was a group of folks who wanted to begin standardizing color measurements. Colorimetry is a word that's sometimes used to describe the measure of color, colorimetry. And one of the many measures, and there are different kinds of measurement systems for quantifying color. But the CIE, I think, works very nicely for us. And here we have a coordinate system that I will probably be asking you about on the exam. So I hope that you'll make a note of this. The coordinate system is one that we have 3 different decimals that will describe any given color. The color of my shirt at a particular point in space, the color of that writing up there, the color of this bluish background, we can use this 3-coordinate system to describe any given color. Okay? And it's very much related to the RGB. These 3 decimals have a constraint. They always have to add up to 1 no matter what. Okay? They always have to add up to 1. Okay? So that's shown here. And we only really need to specify then the first 2 of the 3 because we can then figure out what the remaining 1 would be. Okay, so for example, the first decimal always pertains to the R component in RGB. So if we have a 0.4 for R, okay, and we have a 0.5 for G, and it always goes in that order, that sequence, R, then G, then B. Then the B component would have to be 0.1 because that's how that would add up to 1. Who's following that? That work for us? Okay, that's pretty straightforward. Most students find it pretty straightforward. So when I ask you for RGB coordinates on an exam question, I might ask you to describe something like Denison's big red color. Okay, so you look at the various big reds that we see on people who have baseball caps that say big red, or you see any of our sporting teams that have red. The red that's on our website, okay, that's sort of the school color. Right, we can ask how would you use CIE to describe that. You should always give us 2 coordinates. We know that there are really 3. But the convention is to only specify the 2 because the third one would automatically be determined. Who's following that? Since we only really need the 2, we can always derive the third. Yeah.
Do you always have to have it be some decimal, or can one of the coordinates be 0?
Yes, so it can
So
be
you
between
can
0
do-
and 1. Yeah, it can be 0 and 1 inclusive.
You could do 1, R equals 1, and then the other 2 would be
Yep.
0.
And so if you wanted to give us a really good fire engine red, for example, the CIE coordinates for that would be 1, 0, and nothing more, because we would know that the last one would also have to be a 0. Okay? Suppose it were a really good green, right? 0, 1. Right, if it were perfect green. Yeah, please go ahead first.
For the exam, like, would you, if you asked us to like report, like the different decimals, like, are you going to be picky the values we give them?
No, but it would have to be in the ballpark anyway. Right? I mean, see, we wouldn't necessarily, you're not going to have a light meter on the exam to work with.
Right.
And the light meter actually does give us a CIE coordinates. We'll do a demo with that in just a moment.
Okay.
But what's cool about all of this is that you can make a pretty good approximation. You can get at least the relative strengths of these 3 different guns in a projector, the R, the G, and the B.
Okay.
Okay, let's go with Riella and then also with Jenny.
What's the proper way to like format that when you're writing, say,
Good.
what coordinates are?
Yeah, right, okay. So you can simply list the coordinates and maybe separate them by a comma. So we might say something like the CIE coordinates for the big red stimulus, right? That might be on our website if we were given a question about CIE. And we might have something like red. If that were the prompt, then you might put something like this. Okay. Yeah. So just separate them by a comma. Oh, there was one other hand, I think. Jenny.
That's what I'm
Oh, okay. Yeah, that's neat. So here they are. And you don't even have to put R1, G1, just 1 comma 0. 2 numbers separated by. All right, let's do this then. I'm going to turn on the lights. I'll show you some stimuli. And I want you to yell out some plausible CIE coordinates. Wow, isn't that a spectacular blue when the lights go down? Kind of a sad blue when the lights are up. But okay, let's see what we get here. What do you think?
1,
1, 0. All right, let's go to another stimulus. Let's see if everybody can yell these out.
0, 1.
0, 1. Okay, here's another stimulus.
0, 0.
0, 0. Okay, pretty cool. That's the 0, 0 stimulus in the CIE coordinate system.
Oh, so you wouldn't say 0, 0, 1, you would just say 0, 0.
You see, and why would we do that? So you're
Because
right.
we just assume that it's.
Because it has to add up to 1, right?
Yeah.
That's the only number that's left. Okay. Uh-oh.
Oh gosh.
0.5.
0.5. Perfect. Okay. And that leaves nothing for the blue gun. And a moment ago, when we were making yellow, I think it was Owen who said, hey, take that blue gun out of there, right? He had us turn that all the way down. Okay. All right, see if we've got anything else cooking here. Hey, kind of a gray. 0.3, 0.33, yep. There's a 0.33 repeating in both spaces, okay, because this is chromatic and neutral, right? We're getting equal values of all of those. Okay, and then this was, I would ask you about that. We were going to, at this point, cycle back and try to develop a Hershey bar out of our PowerPoint color wheel, but we did not. We skipped ahead to that, and that's where we ended on Friday. Okay? So that now gives us one of several different types of systems that we can use to describe color. Turn these out one at a time so that it's not too shocking. And there are other kinds of systems, but that's one that we're going to stay with. I think Harshita has a question.
If you use the color meter on, say for example, light,
Uh-huh.
does its coordinates and pigment, would it be different? Same
Actually,
color.
for the same color, you can arrange this so that they're identical. So let me tell you what this thing does. This thing actually records two different kinds of numbers. It gives you the overall level of light expressed in something called candelas per square meter. That's just like the total number of photons. Remember that we had previously these different kinds of filters, and we said something like number of photons on this axis, and it was 100 and 0. Right? We had a lot more than 100 photons. We can have a unit of measure called the candela per square meter, and that's one of the things that comes out of this. The other thing it records for you is the two RGB coordinates, the two CIE coordinates that are going to refer to R and G, and then B is going to be left. Let's do it this way. I wonder if we can turn this thing on. We'll make one of the students the filmer here. You can come on up and shoot this thing. We'll see if we can get you to make different kinds of measures. And we'll see that the numbers that you gave a moment ago were really, really good numbers. When you go to make a physical measurement, though, it's sometimes hard to get this device to corroborate the measure that you were just yelling at. So I'll dial back. Okay. And I'll see if I can show us some really nice chromatic stimuli. Okay. Let's go. Go back this way. And we'll see if one of you would be kind enough to play calibrator for us. I'll turn off the lights. Okay, anybody want to shoot the stimulus? Becca will do it? Okay, thanks. Then we'll have Harsha do it. So the idea, Becca, is to look through this thing and hold down the trigger for a period of time until you'll see the number coming up into your screen from the inside. So you're going to see a big red circle there. If you'll just hold down the trigger, hold it down for a couple of seconds in a row, and then at some point, numbers will appear on the screen.
16.3.
Okay, so what that's telling us is right now she's getting 16.3 candelas per square meter. Can you let the meter go just for a second? Can you now flip the meter around to this side? And if you look over here, Becca, can you tell us what two numbers? I might need to turn these lights on for you to see it. Can you make those out?
0.577 and 0.331.
Okay, 0.577 and 0.331. So you and I describe this as being 1, 0. Who remembers that? Okay. Our light meter tells us it's 0.577 and
331.
331. Okay. Any ideas as to why that thing is screwed up? Actually, that thing is probably correct. But why would that be not giving us 1, 0? Any notion about that? That projector is set to be putting out 255 in red and nothing else in green, nothing else in blue. Right? So we just have red coming out of that. And yet we're not getting 1, 0, we're getting 0.57 and 0.3 something. Any notion about that?
It's also being reflected off of another surface.
It's being reflected off another surface. What color was that surface?
White.
It was white, okay. What color, if I can be vulgar, is coming through the window? Everything's coming through the window. And when everything comes through the window, what are the RGB or the CIE coordinates for everything that's coming through the window? If it's white light, okay, so we have a mixture of a really strong red coming in that way, and all this ambient light that is 0.33, 0.33, and 0.33. So we should get something other than 1, 0, but it will be leaning toward the red. And those numbers again were 0.57 and 0.3 or something. Okay.
Yeah.
Becca, can you stay with us one more time? Let's change it now, and we'll have you be a photographer. And so everybody in the class, what did we say this color was in CIE? 0, 1. People okay with that in CIE? We'll let Becca take a measure. This might be brighter in total number of lumens, perhaps.
It says 97.5.
Okay, so we were at 13 or something a moment ago.
Yeah.
Okay, now Becca, if you spin it around and look on the side of your panel,
Can I
you'll be
let
able to
go?
Yeah, you can let that go.
0.369 and 0.582.
Okay, so those almost reversed, right?
Yeah.
So it was 0.5 a moment ago and 0.3, and now we put up this stimulus and the 0.3 and the 0.5 reverse, okay? But still we have all the white light that's coming in here, and all the ambient light that's coming in from that window as well. Just following that worked for us. Let's see how we do on this relatively, hopefully we'll get something that's more like a neutral stimulus. Can you shoot? We'll make this last one. And when you get a number there,
We got 121.
okay, so that's a lot of light there.
This one is .314 and .361.
Okay, so that's pretty close, right? All right. So we actually do have maybe slightly more green in there than we had red, to use the Volga, but that's pretty close. All right. Thank you, Becca.
Yeah.
All right, thanks very much. A few other folks wanted to play with that. I'll leave that up here so we can take some more measurements later. But that's a pretty neat device. Yeah, please go ahead. Is that just a stretch? Okay,
Yeah.
I thought I saw your hand up. Okay, good. Questions or comments on CIE coordinates? Okay, let's do this then. Let's see if we can get into today's conversation on color. That was finishing up Friday's conversation on color. Let's see if we can have you respond to 3 questions. I'm going to ask you to jot, we will make this a pop quiz, but I hope you'll take out a blank sheet of paper, and I'll give you what I hope is a fairly simple question, and then 2 other questions that are a little bit more challenging. We'll see how you'll respond to these questions.
We're not turning this into.
You're not turning this in. Nope, you don't get to just later box. It's not a quiz. This is just a conversation. Okay, the first question I hope is really simple. The first question is, can you define for us what a metamer is? Give us the definition of a metamer. We've mentioned it a few times today. This is pure memorization, and we're going to build on it. But we'll start out with just making sure everybody's really clear on what the metamer is. You've got something down on that. Okay, now what I'd like you to do is think about this next question that will be related to metamers. Can you draw a graph that demonstrates how a monochromat is vulnerable to color members? So you and I are trichromats, but some other, at least under most lighting conditions, we are trichromats. Under certain lighting conditions, we are monochromatic. So the question becomes, can you draw a graph that demonstrates how a monochromat is vulnerable to metamers? That's easier to do if you know what a metamer is. That's why we had question 1 as we did. So we need a graph that shows how monochromats are vulnerable to metamers. Now, I love questions like that as test questions because they implicitly test that you know what a monochromat is, they implicitly test that you know what a metamer is, and they also have you think through the relationship between that and express it graphically. So there's a lot going on in that question. Some critical reasoning, and also some vocabulary knowledge. Metamer, monochromat. Okay, then when you're finished with that, I wonder if I can bring you to the third question. It's okay if you're still working. The third question will be similar to the second question, but here's question number 3. Can you draw a graph that demonstrates how a dichromat is vulnerable to color members? So question number 2 is about the monochromat. Question number 3 will be about the dichromat. Question 1 is, what is a metamer? So now we need a dichromat. And most mammals are dichromatic. We're a little bit unusual, we primates. weeks when we talked about acoustic energy. Okay, some people are still writing, and that's all fine. I wonder if we might do something that's a little bit different today. Could we get one or two brave souls to come up and put an imperfect graph? It's important that it be imperfect, although we'll let you slide if it turns out to be perfect. But I'm looking for an imperfect graph. Up on the board, anybody want to grab some chalk and try to get it going? Would somebody move it? Thank you.
I can do number 3.
Oh, number 3. Okay, that works. Yeah, if you could, why don't we get, maybe we can do over on this side-ish, we can get the dichromatic going. And there's chalk from that side. Do you have something, Owen? If you would mind
Or
getting-
I can get them modified.
Okay, that works. That works. Thank you. We'll grab something. And these don't have to be perfect, but they'll get the ball rolling.
So are they perfect? Are they purposely imperfect, or?
No, make them as best as you can.
Okay.
If it turns out that they don't quite work, that's okay. That was an attempt to reduce people's anxiety. Some people are still writing on their own, they're drawing their own graphs at school. While Owen and Harshita are doing that, can we just have a little bit of conversation? Can we remind ourselves of what the metamer is? So what do we think about that? Jenny's got something.
It's like two different physical stimuli that, two different physical stimuli that are perceptually identical.
Okay, very good. Two physically different stimuli that are perceptually identical or perceptually indistinguishable. So one more time, what would my d prime need to be for me to say that I've got a metamer?
It's very small.
It would have to be very small, maybe close to 0, right? I can't discriminate stimulus 1 from stimulus 2. My capacity to make a same different judgment will be not really greater than chance. So my d prime is going to be 0. Okay? So, and we're going to see that we have all kinds of metamers in different kinds of sensory systems. Right now we're in vision. Right now we're specifically in color within vision. Wow, these are looking really good. And this is something we explained on the video, and we actually have a couple of PowerPoint slides that we can put up as well to understand these. I really like to do these questions sort of one at a time because through the years I find that the graphs that are in this particular PowerPoint presentation for today are the ones that students have historically reported the most difficulty in understanding. And so you might notice that today's video was quite short. It was only like 12 or 13 minutes long. And typically these graphs do require a little bit of thought, and they're a little counterintuitive to some students. Okay? But they're a good way to get going. So we have our definition then of metamers as these physically different stimuli that are perceptually indistinguishable. Okay? Let's start out with Harshita's over here. First, Harshita has it appropriately labeled. Somebody other than Harshita, what does this thing stand for? Wavelength, okay, and it's also the Greek letter, June had the Greek letter, it's called lambda, and it stands for wavelength. And we can have a range that might go from 400 to 700, okay, real good. I wonder if I can impose on Harshita. That looks really good. Can you help walk us through? You can stay right there.
Okay. Okay. The y-axis is percentage light absorbed.
Percent of light absorbed.
Those are supposed to be 25, 50, 75. The marks
Got
on
it.
the
25,
y-axis,
50, 75. Thank you. Okay.
approximately.
Well done. Well done.
Since it's a dichromat, it has 2 pigments. The left one is pigment 1.
Okay.
The right one is pigment 2.
All right.
My handwriting on boards is not good.
Nope, that's
So-
better than mine. So thank you.
Yes.
Pigment 1, pigment 2.
Pigment 1, pigment 2. A and B are 2 wavelengths
Okay.
at which we're measuring response of the 2 pigments.
Okay.
And since it's going to be the same at the 2, the percentage light absorbed, you get a white response because percentage light absorbed is the same.
Okay. I think I'm following you there. I might have lost it there. I really like this. This is broadband.
Yes.
Okay, that's broadband. Okay. So
Yeah.
let's think about a really broadband light here. Okay. If we had a really broadband light, we would get the same amount of absorption, and she has this beautifully labeled, the percent of light absorbed. We'd get the same amount of light absorbed in pigment 1 as we would in pigment 2. Who's okay with that? And I want to make sure that people are okay with that before we move on. It's completely reasonable if you're not okay with that. Okay? So you have really broadband light, and this is even broad enough here. We're getting, if we use the full broadband light, pigment 1's excitation or absorption rate will be equal to pigment 2's excitation rate. People okay with that? Yep, all right, that works. So if we were to put the ratio of light absorbed of pigment 1 over pigment 2, that number would equal 1. Whatever that fraction turns out to be, if it were 0.5 over 0.5, that would equal 1. If it were 0.73 over 0.73, that would equal 1. If it's 0.9 over 0.9, that equals 1. So the broadband light generates a ratio of 1. Who's cool with that? Does that work for us? Okay. And then can you bring us over to here?
Okay.
Okay, the center spike.
With the same individual, if you put a monochromatic laser at that wavelength where the graphs intersect,
Perfect.
you'd find again that the responding is the same
Okay.
for both, and you would get a white perception.
That's perfect, okay? So if we happen to put a single laser, which just has a single wavelength of light, it's perfectly focused light, perfectly saturated, to use our earlier terminology, maybe that's only going to be 25, but remember, it's 0.25 for pigment 2. It's also 0.25 for pigment 1. 0.25 over 0.25 equals 1. 0.25 over 0.25 equals 1. Okay, one number over that same number will always equal 1. So we're getting a similar ratio from this wavelength of light as we would from this really broadband light. And this is a laser, this is broadband, those are wildly different stimuli. Okay, they're physically different, but they're perceptually indistinguishable because Harshida has drawn this correctly. And this actually describes a whole lot of mammals. It describes your cat and your dog. Like your cat and your dog might have slightly, maybe your cat is slightly further apart like this, and your dog is more like this, or vice versa, but they aren't dichromatic. And that's the key feature that's captured here. Okay, a couple of questions. We'll go with Lise first, and then with Emily.
What was the ratio that you equaled around again? Commercial light.
Can you flip me a number? Flip me a number between 1 and 100.
70.
70?
Yeah.
70 over 70 equals 1?
Yeah.
Okay, all right. So if it were the case that we had just this monochromatic light, okay, we're getting this level of absorption in pigment 2, and we're getting that same level of absorption. So yeah, it could have been, I was thinking that might be 0.25-ish over 0.25. I'll write it here. Yeah, does that work for us? Okay. Emily also had a question. And then
Yeah,
we'll
just a quick question. So a kind of crucial point in the graph is the intersection between the laser and the two pigments.
That's right. Yeah, you do it better than I would have drawn it, so thank you. Real good. Owen, and then maybe Becca.
So not only the saturated laser right down where the lines intersect, but any combination of frequencies that stimulates the cones the same will be a metamer of broadband light.
Yeah, that was beautifully verbally expressed, and those of you who couldn't see that, Owen was doing this with his hands. So I can pick now, I can pick a combo of lasers, and I can have one right here and one right here. And now I'm going to get 75 over 75, okay, from those two lasers. That would do the trick. Oops, excuse me. 75 over 75. Okay. I can take some that are way out here. I can take a really short wavelength light, a really long one. But if I hit it just right, I'm still going to get now 0.04 over 0.04. That'll give me one. So any combination will do the trick. But what's really cool is that we can fool this system even with just one light. Right? I mean, it can't distinguish the ultimate thin light from the broadest of all possible lights. That's a pretty big metaphor. You can't distinguish those two wildly different spectra. Completely broadband, completely localized. You get the same perceptual response because you're getting the same biological response. Okay, Becca had something to do?
I just realized mine had to do with monochromats. So
Okay, good. Hey, and we've got 3 minutes left to do the monochromats, but I think we can do it. We'll do monochromacy in 3 minutes. It's actually easier. I wonder if Owen could begin to walk us through?
All right, so the axes of this graph are the same as Harshey does. You have the wavelength on the x-axis, and then the quantal catch on the y.
Which is the same thing as percentage of light absorbed. How many quanta or photons are we catching? So thank you.
So our one photoreceptor is going to have a certain ability to capture different wavelengths of light. And we have a wavelength A that this cone can catch about 25% of the time. And then we have wavelength B that it can catch 50% of the time.
Perfect.
So the thing about monochromats is if you have twice as many photons of A as you do of B, it's going to be the same psychological phenomenon for them that's going to be
Perfect. Very, very good. Just beautifully explained. Let's see if everybody is okay with that. How many people think they're following that description? Anybody a little bit lost? That one sometimes confuses some folks. Thank you for being honest. Folks are a little bit lost. First, Owen's picture and description, just like Harshi's, was spot on. So thank you both for that. Okay, so what we're going to do now is we only have one pigment as opposed to two pigments. Who's okay with that? So mono and dye, and then you and I are trying. And by the way, before we call it a day, I did want to put up this one. Here are damselflies that Dr. Schultz has measured, and they have 4 of these. Okay? So the damselflies that are floating out there in the vinyl reserve, we have 3 like us, 2 like your dog, 1, probably some invertebrates might have 1, but here we have some damselflies that have 4. Okay? 4 different kind types. Okay, we'll go back over to here and see if we can understand the point that Owen's making. Let's get to do some mathematics with this. Let's say that I have a light over here at A, it's a monochromatic light, and I'm going to turn its intensity up to 100. Okay? How many photons will I absorb if I have 100 photons coming out at you? How many will I actually catch? 25. If I have 100 coming out at this wavelength, that's my intensity. How many will you actually catch? 50. Who's all right with that? Let's play that game one more time. I send you 100 and we're at B, and you get 50. Okay, now here's the trick. Now I'm going to send you 200 units of light at wavelength A. How many will you catch now?
50.
So you can catch 50 over here if I start out at 200, and 50 over here if I start out at 100. So by changing the intensity of the light, I'm getting the same response out of this thing. Okay? And it now can't distinguish a wavelength change from an intensity change. By changing from 100 to 200, I've changed the intensity, but not the wavelength. But now, either way, I'm going to wind up with catching 50 photons. So I'm going to get 50 of these cis-trans isomerizations over here at A. I change the wavelength, and I change the intensity, and I get the same 50 cis-trans isomerizations. So this guy is not particularly good at discriminating wavelengths from intensity. Please go ahead.
Just one quick question. If like the stimulus A in that graph was just moved slightly further to the right, where we also catch 50 like photons each time, would that mean that they're still like, indistinguishable to a monochromatic?
Yeah, so this is the monochromatic, right? So if we move this over here to catch 50 left of center and 50 right of center, we have a wavelength change that is indiscriminable to this, so that those would be metameric also.
Okay.
Yep. So what's cool about this is we can also throw intensity in here. We're at 9:21. Some people have to get to a 9:30 class. We'll draw the line there. I'm happy to go over this again at the beginning of next time. We're also getting into form perception. So we're finishing up color today, and we'll be talking about form perception. Thanks for the good participation, and I look forward to seeing some of you Tuesday. Keep an eye on your Slater box. Your responses are there for your good writing assignments. Sure.
So we used the example earlier in Friday's PowerPoint about there was the girl with the color on her face and she had a really bad would a monochromatic detect?
I can do that.
All they've got is
It's the last day before.
So they would perceive that as like all one.
I can do that.
You have to actively write something, even if I can't read it. It's fine. You care.
Sponsors, we're gonna write that because we know that there's
I'm going to have one of those students there, so that you can come at times.
Yeah.
Okay, because I never really know who's going to
We
show up.
don't need to stay where we are. I've only read kind of slightly.
Yeah.
Is that something that can be available?
Yeah, I think so. If you search for Dalton on BBC, Dalton Colorblind Monkey.
Okay, I was looking at it on YouTube, I wasn't sure where.
Yeah, there's a couple of variations on it. It's only like a 30-second video.
Oh, okay.
All right? All right, hey.
Hey, with this,
Yeah.
when you change intensity, I'm just trying to relate it back to the first lecture we did on color.
Yeah.
Is that brightness?
Yes,
Is that the same thing as brightness?
intensity is perceptual correlate is brightness. So intensity and brightness go together. Please come on in.
Okay.
Yep.
And I saw on the PowerPoint slides that there's one about the blind watchmaker that I have to click on.
PowerPoint slide about the blind watch. Oh, you have a PowerPoint about the blind watchmaker?
Yeah, that we haven't really gone through in class. Do you?
You might remember that we had 7 questions or so in the blind watchmaker.
Yes.
And those are the 7 that are on PowerPoint.
Oh no, there was another one.
There's another one.
It's called supplement something.
Did we do the Miller experiment very briefly?